Welcome, everyone, to a soothing journey into the heart of electrochemistry. Tonight, we're not just exploring the science of batteries and supercapacitors. We're uncovering their hidden world as you drift off to sleep. Imagine the intricate dance of electrons, the silent reactions powering our devices, all while you rest peacefully. Let's delve into this fascinating realm where science meets serenity. Our focus tonight is on rechargeable batteries, those ubiquitous powerhouses that fuel our smartphones, laptops, and even electric vehicles. But have you ever stopped to consider what really happens inside a battery when you're not using it, especially while you sleep? The answer lies in the complex interplay of chemical reactions and physical processes that continue even when the battery is at rest. We'll uncover these secrets, making the science accessible and calming, perfect for a bedtime story of electrons and ions. To begin, let's visualize the anatomy of a lithium-ion battery, the most common type of rechargeable battery today. Picture a sandwich with two slices of bread representing the electrodes, the anode, negative electrode, and the cathode, positive electrode. Between these slices lies the electrolyte, a special sauce that allows lithium ions to move back and forth. When the battery is charging, lithium ions travel from the cathode to the anode, storing energy. When discharging, they flow back, releasing energy to power your device. It's a reversible dance, a delicate equilibrium that allows us to recharge and reuse the battery countless times. Now, consider what happens when you plug your phone in before bed. The charging process is an orchestrated series of electrochemical reactions. At the cathode, lithium ions are extracted from a lithium compound, such as lithium cobalt oxide, LiCoO2, and migrate through the electrolyte. Simultaneously, electrons flow through the external circuit, providing the energy needed to drive this process. At the anode, typically made of graphite, lithium ions are inserted between the layers of carbon atoms, a process called intercalation. This insertion is not merely a physical lodging. It's a chemical bonding, a subtle embrace between lithium ions and the carbon structure. But what governs this movement, this flow of charge? It's all about electrochemical potential, the driving force that dictates the direction of ion and electron movement. Think of it like a hill. Ions and electrons naturally want to roll downhill from a region of high potential energy to a region of low potential energy. During charging, the external power source creates this hill, pushing the lithium ions uphill from the cathode to the anode. Once charged, the battery stores this potential energy, ready to release it when needed. The beauty of a rechargeable battery lies in its reversibility. Unlike primary batteries, which are disposable, rechargeable batteries can undergo this charge-discharge cycle hundreds or even thousands of times. This is due to the unique properties of the electrode materials and the electrolyte, which allow for the efficient and reversible movement of lithium ions. However, this process is not perfect. With each cycle, tiny changes occur within the battery, leading to gradual degradation and reduced performance. This is why your phone's battery life diminishes over time. let's take a moment to appreciate the historical context of battery technology. The story begins with Alessandro Volta, an Italian physicist who invented the first true battery in 1800. Volta's pile, as it was called, consisted of alternating discs of zinc and silver separated by brine-soaked cardboard. This simple device produced a continuous electric current, a groundbreaking achievement that paved the way for modern electrochemistry. Volta's invention sparked a flurry of research, leading to the development of various battery types, each with its own advantages and limitations. Fast forward to the 20th century, and we encounter the lithium-ion battery, a revolutionary technology that transformed portable electronics. Developed in the 1970s and commercialized in the 1990s, the lithium-ion battery offered unparalleled energy density, meaning it could store more energy for its size and weight compared to previous battery technologies. This breakthrough enabled the miniaturization of electronic devices, making smartphones, laptops, and tablets a reality. The development of the lithium-ion battery was a triumph of materials science and electrochemical engineering, a testament to human ingenuity. Now, let's return to our sleeping battery. Even when your device is idle, subtle processes are still at play. One such process is self-discharge, a gradual loss of charge due to internal chemical reactions. Imagine tiny currents leaking within the battery, slowly draining its energy. This self-discharge is influenced by temperature, battery chemistry, and manufacturing quality. Higher temperatures accelerate self-discharge, which is why it's not a good idea to leave your phone in direct sunlight. Similarly, impurities or defects within the battery can create pathways for unwanted reactions, leading to faster self-discharge. Another phenomenon that occurs in a sleeping battery is the formation of a solid electrolyte interface, SEI, layer. This layer forms on the surface of the anode due to reactions between the electrolyte and the lithium ions. The SEI layer is both a blessing and a curse. On one hand, it protects the anode from further corrosion and degradation, extending the battery's lifespan. On the other hand, it increases the battery's internal resistance, hindering the flow of lithium ions and reducing performance. The formation and evolution of the SEI layer are complex processes that scientists are still trying to fully understand. To further illustrate these concepts, let's consider a real-world example: an electric vehicle EV battery. EV batteries are essentially large packs of lithium-ion cells, carefully arranged and managed to provide the power and range needed for driving. When an EV is parked overnight, its battery continues to undergo self-discharge and SEI layer formation, albeit at a slower rate than when in use. The Battery Management System, BMS, monitors these processes, ensuring that the battery remains within safe operating limits. The BMS also balances the charge between individual cells, preventing overcharging or overdischarging, which can damage the battery. Supercapacitors, also known as ultracapacitors or electrochemical capacitors, represent a different approach to energy storage. Unlike batteries, which store energy through chemical reactions, Supercapacitors store energy electrostatically by accumulating ions on the surface of an electrode. Imagine two parallel plates immersed in an electrolyte with a thin separator between them. When a voltage is applied, ions from the electrolyte migrate to the surface of the electrodes, forming an electrical double layer. This double layer stores energy, much like a capacitor in an electronic circuit. The key advantage of supercapacitors is their ability to charge and discharge very quickly, much faster than batteries. This is because the energy storage process is purely electrostatic, without the need for chemical reactions. Supercapacitors can also withstand hundreds of thousands or even millions of charge-discharge cycles, far more than batteries. However, supercapacitors have a lower energy density than batteries, meaning they can store less energy for their size and weight. This makes them suitable for applications where rapid charging and discharging are required, such as regenerative braking in hybrid vehicles or burst power delivery in electronic devices. Let's delve deeper into the materials science behind batteries and supercapacitors. The performance of these devices depends critically on the properties of the electrode materials and the electrolyte. For lithium-ion batteries, common cathode materials include lithium cobalt oxide, LiCoO2, lithium manganese oxide, Lim2O4, and lithium iron phosphate, LiFePO4. Each material has its own advantages in terms of energy density, power density, and cycle life. Anode materials typically consist of graphite, although researchers are exploring alternative materials such as silicon and lithium titanate, Li4T5012, to improve energy density. The electrolyte plays a crucial role in facilitating the movement of lithium ions between the electrodes. It must be chemically stable, have high ionic conductivity, and be compatible with the electrode materials. Common electrolytes consist of lithium salts dissolved in organic solvents, such as ethylene carbonate, EC, and dimethyl carbonate, DMC. However, these electrolytes are flammable and can pose safety risks. Researchers are developing solid-state electrolytes, which are non-flammable and offer improved safety and performance. Solid-state batteries, which use solid-state electrolytes, are considered the next generation of battery technology. To better understand the science of electrochemistry, let's consider a simple analogy: a water reservoir. Imagine a reservoir filled with water, representing the energy stored in a battery or supercapacitor. The height of the water level represents the voltage, while the amount of water represents the charge. Pumping water into the reservoir is like charging the battery, while releasing water from the reservoir is like discharging the battery. A battery is like a large reservoir that can store a lot of water, but it takes time to fill and empty. A supercapacitor is like a small reservoir that can be filled and emptied very quickly, but it can't store as much water. Let's explore some of the cutting-edge research in the field of electrochemistry. Scientists are constantly striving to improve the performance, safety, and cost of batteries and supercapacitors. One promising area of research is the development of new electrode materials with higher energy density and longer cycle life. For example, researchers are exploring the use of nanomaterials, such as carbon nanotubes and graphene, to enhance the performance of electrodes. These materials have high surface area and excellent electrical conductivity, which can improve the rate of lithium-ion transport and increase energy storage capacity. Another area of active research is the development of new electrolytes with improved safety and performance. Solid-state electrolytes are particularly promising, as they are non-flammable and can enable the use of high-energy density electromaterials. Researchers are also exploring the use of ionic liquids, which are organic salts that are liquid at room temperature. Ionic liquids have high ionic conductivity and wide electrochemical windows, making them attractive candidates for electrolytes in batteries and supercapacitors. Now, let's consider the environmental impact of batteries and supercapacitors. The production and disposal of these devices can have significant environmental consequences. The mining of raw materials, such as lithium and cobalt, could disrupt ecosystems and displace communities. The manufacturing process can consume large amounts of energy and water, and the disposal of spent batteries can lead to pollution if not done properly. It's important to recycle batteries and supercapacitors to recover valuable materials and prevent environmental contamination. Many countries have implemented battery recycling programs to encourage responsible disposal. To further illustrate the importance of electrochemistry, let's consider its applications beyond batteries and supercapacitors. Electrochemistry plays a crucial role in various industries, including corrosion prevention, electroplating, and chemical synthesis. Corrosion is the degradation of materials due to chemical reactions with their environment. Electrochemical techniques can be used to protect metals from corrosion, such as by applying a protective coating or using cathodic protection. Electroplating is the process of coating a metal object with a thin layer of another metal, using electrochemical deposition. This is used to improve the appearance, durability, or corrosion resistance of the object. Let's take a moment to appreciate the scientists and engineers who have contributed to the field of electrochemistry. Their dedication and ingenuity have led to countless innovations that have transformed our world. From Alessandro Volta's invention of the first battery to the development of the lithium-ion battery, these pioneers have pushed the boundaries of scientific knowledge and technological progress. Their legacy continues to inspire researchers and engineers today as they strive to create even better energy storage devices. As you drift off to sleep, remember the intricate dance of electrons and ions within the batteries that power your devices. These silent reactions are a testament to the power of electrochemistry, a science that continues to shape our world. From electric vehicles to renewable energy storage, electrochemistry holds the key to a sustainable future. So rest easy, knowing that even as you sleep, the world of science is working tirelessly to improve our lives. Let's consider a more specific example: the charging process of a smartphone battery. When you plug your phone into a charger, you're initiating a complex series of electrochemical reactions within the battery. The charger provides a voltage that drives lithium ions from the cathode to the anode, storing energy in the process. The charging process is carefully controlled by the phone's battery management system, BMS, which monitors the voltage, current, and temperature of the battery. The BMS adjusts the charging rate to optimize charging speed and prevent overcharging or overheating. Once the battery is fully charged, the BMS terminates the charging process to prevent damage. To further illustrate the role of the electrolyte, let's consider its properties in more detail. The electrolyte must be chemically stable, meaning it doesn't decompose or react with the electrode materials. It must have high ionic conductivity, meaning it allows lithium ions to move easily through it. And it must be compatible with the electrode materials, meaning it doesn't corrode or dissolve them. The electrolyte also plays a role in the formation of the SEI layer, which protects the anode from further degradation. The composition and properties of the electrolyte are carefully optimized to achieve the best possible battery performance. Now, let's consider the challenges and opportunities in the field of electrochemistry. One of the biggest challenges is improving the energy density of batteries. Energy density is the amount of energy that a battery can store for its size and weight. Higher energy density means longer battery life and smaller, lighter devices. Researchers are exploring various approaches to improve energy density, such as developing new electrode materials with higher capacity and using high-voltage electrolytes. Another challenge is improving the safety of batteries. Batteries can be flammable and can explode if overcharged or short-circuited. Researchers are developing solid-state electrolytes and other safety features to prevent these hazards. Another opportunity in the field of electrochemistry is the development of new types of energy storage devices. Supercapacitors are one example, but there are other emerging technologies such as flow batteries and metal-air batteries. Flow batteries store energy in liquid electrolytes that are pumped through a stack of electrochemical cells. Metal-air batteries use oxygen from the air as the cathode material, which can significantly increase energy density. These new technologies have the potential to revolutionize energy storage and enable new applications, such as grid-scale energy storage and long-range electric vehicles. Let's delve into the economic aspects of battery technology. The battery industry is a multi-billion-dollar market driven by the growing demand for portable electronics, electric vehicles, and renewable energy storage. The cost of batteries has been declining steadily over the past decade, thanks to technological advances and economies of scale. However, batteries still represent a significant portion of the cost of electric vehicles and other applications. Further cost reductions are needed to make these technologies more affordable and accessible. The battery industry is also creating new jobs and economic opportunities in manufacturing, research, and recycling. To better understand the role of electrochemistry in corrosion prevention, let's consider some specific examples. One example is the use of sacrificial anodes to protect pipelines from corrosion. Sacrificial anodes are made of metal that is more easily corroded than the pipeline material, such as zinc or magnesium. The sacrificial anode is connected to the pipeline, and it corrodes instead of the pipeline, protecting it from corrosion. Another example is the use of protective coatings to prevent corrosion. Protective coatings, such as paint or epoxy, create a barrier between the metal surface and the corrosive environment. These coatings can be applied by various methods, including spraying, brushing, or electrodeposition. Now, let's consider the future of electrochemistry. The field is rapidly evolving, driven by the need for better energy storage devices and sustainable technologies. New materials, new designs, and new applications are constantly emerging. The future of electrochemistry is bright, with the potential to transform our world in countless ways. From powering our homes with renewable energy to driving our cars with electricity, electrochemistry will play a crucial role in creating a cleaner, more sustainable future. Let's consider the role of electrochemistry in medical devices. Electrochemical sensors are used to monitor various physiological parameters, such as blood glucose levels, oxygen levels, and pH levels. These sensors are used in a variety of medical devices, including glucose meters, blood gas analyzers, and implantable medical devices. Electrochemical techniques are also used in drug delivery systems, such as transdermal patches and implantable drug pumps. These systems use electrical currents to control the release of drugs into the body. Electrochemistry is also used in medical imaging techniques, such as electrochemical impedance spectroscopy, which can be used to diagnose diseases and monitor tissue health. To further illustrate the importance of electrochemistry in chemical synthesis, let's consider some specific examples. Electrochemistry can be used to synthesize a wide range of organic and inorganic compounds, including pharmaceuticals, polymers, and nanomaterials. Electrochemical synthesis offers several advantages over traditional chemical synthesis methods, such as milder reaction conditions, higher selectivity, and lower environmental impact. Electrochemical techniques are also used in the production of chlorine and sodium hydroxide, which are important industrial chemicals. These chemicals are produced by the electrolysis of brine, salt water. Now, let's consider the challenges of scaling up battery production. As the demand for batteries increases, it's important to be able to manufacture them at a large scale and at a low cost. Scaling up battery production involves several challenges, such as ensuring the availability of raw materials, optimizing the manufacturing process, and maintaining quality control. The battery industry is investing heavily in new manufacturing facilities and technologies to meet the growing demand. Automation, robotics, and artificial intelligence are being used to improve the efficiency and precision of battery manufacturing. Let's delve into the role of electrochemistry in fuel cells. Fuel cells are electrochemical devices that convert the chemical energy of a fuel, such as hydrogen, into electrical energy. Fuel cells offer several advantages over traditional combustion engines, such as higher efficiency, lower emissions, and quieter operation. Fuel cells are used in a variety of applications, including transportation, stationary power generation, and portable power. The development of fuel cells is an active area of research with the goal of improving their performance, durability, and cost. Electrochemistry plays a crucial role in understanding and optimizing the performance of fuel cells. To better understand the science of supercapacitors, let's consider their applications in more detail. Supercapacitors are used in hybrid vehicles to provide regenerative braking, which captures energy during braking and stores it for later use. Supercapacitors are also used in electric buses and trains to provide rapid acceleration and deceleration. Supercapacitors are used in electronic devices, such as smartphones and laptops, to provide burst power delivery for applications such as camera flashes and wireless communication. Supercapacitors are also used in energy harvesting systems to store energy from renewable sources, such as solar and wind. Now, let's consider the ethical implications of battery technology. The mining of raw materials for batteries can have negative social and environmental consequences. It's important to ensure that these materials are sourced responsibly and ethically. The battery industry is working to improve its supply chain practices and promote responsible sourcing. The disposal of spent batteries can also have ethical implications. It's important to recycle batteries to recover valuable materials and prevent environmental contamination. Battery recycling programs should be accessible and convenient for consumers. To further illustrate the importance of electrochemistry in renewable energy storage, let's consider some specific examples. Batteries are used to store energy from solar panels and wind turbines, allowing this energy to be used when the sun isn't shining or the wind isn't blowing. Batteries are also used to stabilize the electricity grid by providing a buffer between the fluctuating supply of renewable energy and the demand for electricity. Electrochemical techniques are used to develop new materials and designs for batteries that can store more energy and last longer. The development of better batteries is crucial for enabling a transition to a renewable energy future. Let's take a moment to appreciate the beauty and elegance of electrochemistry. It's a science that combines chemistry, physics, and engineering to create devices that power our world. From the smallest batteries in our smartphones to the largest batteries in our electric vehicles, electrochemistry is all around us. It's a science that is constantly evolving, with new discoveries and innovations being made every day. As you drift off to sleep, remember the power and potential of electrochemistry, a science that is shaping our future. Now, let's consider the role of electrochemistry in water purification. Electrochemical techniques can be used to remove pollutants from water, such as heavy metals, organic compounds, and bacteria. Electrochemical water purification offers several advantages over traditional methods, such as lower energy consumption, higher efficiency, and lower environmental impact. Electrochemical techniques are also used in desalination, which is the process of removing salt from seawater to produce fresh water. Electrochemical desalination offers a sustainable and cost-effective way to provide fresh water to communities that lack access to it. To better understand the science of corrosion, let's consider some specific examples. One example is the corrosion of iron, which is commonly known as rust. Rust is formed when iron reacts with oxygen and water, forming iron oxide. Rust weakens the iron and can eventually cause it to crumble. Another example is the corrosion of aluminum, which is a more complex process. Aluminum forms a thin layer of aluminum oxide on its surface, which protects it from further corrosion. However, this layer can be damaged by certain chemicals, leading to corrosion. Electrochemical techniques are used to study and prevent corrosion in various materials. Now, let's consider the role of electrochemistry and sensors. Electrochemical sensors are used to detect a wide range of substances, including gases, liquids, and solids. Electrochemical sensors offer several advantages over other types of sensors, such as high sensitivity, selectivity, and accuracy. Electrochemical sensors are used in a variety of applications, including environmental monitoring, medical diagnostics, and industrial process control. Electrochemical techniques are used to develop new materials and designs for sensors that can detect even smaller concentrations of substances. Let's delve into the challenges of recycling lithium-ion batteries. Recycling lithium-ion batteries is a complex process due to the variety of materials used in the batteries and the potential for hazardous materials to be released. The recycling process typically involves disassembling the batteries, separating the different materials, and recovering the valuable materials, such as lithium, cobalt, and nickel. The recycling process can be energy-intensive and can generate waste. However, recycling lithium-ion batteries is crucial for conserving resources and preventing environmental contamination. New technologies are being developed to improve the efficiency and sustainability of battery recycling. To further illustrate the importance of electrochemistry in the development of new materials, let's consider some specific examples. Electrochemical techniques are used to synthesize nanomaterials, such as nanoparticles, nanowires, and nanotubes. These materials have unique properties that make them useful in a variety of applications, including electronics, medicine, and energy storage. Electrochemical techniques are also used to modify the surface of materials to improve their properties or add new functionalities. Electrochemical deposition is used to create thin films of materials with precise control over their thickness and composition. The development of new materials is crucial for advancing technology and improving our lives. Now, let's consider the future of energy storage. The demand for energy storage is growing rapidly, driven by the increasing use of renewable energy and electric vehicles. New technologies are being developed to meet this demand, including advanced batteries, supercapacitors, and other energy storage devices. The future of energy storage is bright, with the potential to transform our world and create a more sustainable future. Electrochemistry will continue to play a crucial role in the development of new and improved energy storage technologies. Let's consider the role of electrochemistry in the development of new medical treatments. Electrochemical techniques are being used to develop new treatments for cancer, neurological disorders, and other diseases. Electrochemical therapy involves using electrical currents to kill cancer cells or stimulate nerve cells. Electrochemical drug delivery involves using electrical currents to deliver drugs to specific locations in the body. Electrochemical sensors are used to monitor the effectiveness of these treatments. The development of new medical treatments is a challenging but rewarding area of research, and electrochemistry is playing an increasingly important role. To better understand the science of electroplating, let's consider some specific examples. Electroplating is used to coat jewelry with a thin layer of gold or silver to improve its appearance and durability. Electroplating is used to coat car parts with a layer of chromium to protect them from corrosion and improve their appearance. Electroplating is used to coat electronic components with a layer of gold or silver to improve their conductivity and prevent corrosion. The electroplating process involves immersing the object to be coated in a solution containing ions of the metal to be deposited. An electrical current is passed through the solution, causing the metal ions to be deposited on the surface of the object. The thickness and composition of the coating can be precisely controlled. Now, let's consider the role of electrochemistry in the development of new sensors for environmental monitoring. Electrochemical sensors are used to monitor air quality, water quality, and soil quality. These sensors can detect a wide range of pollutants, including gases, heavy metals, and organic compounds. Electrochemical sensors offer several advantages over other types of sensors, such as high sensitivity, selectivity, and accuracy. Electrochemical techniques are used to develop new materials and designs for sensors that can detect even smaller concentrations of pollutants. The development of better sensors is crucial for protecting our environment and ensuring a healthy future. Let's delve into the challenges of developing solid-state batteries. Solid-state batteries offer several advantages over traditional lithium-ion batteries, such as improved safety, higher energy density, and longer cycle life. However, developing solid-state batteries is a challenging task. One of the biggest challenges is finding solid electrolytes that have high ionic conductivity and are chemically stable. Another challenge is ensuring good contact between the solid electrolyte and the electrodes. Researchers are exploring various approaches to overcome these challenges, such as developing new solid electrolytes and using novel manufacturing techniques. The development of solid-state batteries is a promising area of research with the potential to revolutionize energy storage. To further illustrate the importance of electrochemistry in the development of new energy storage devices, let's consider some specific examples. Electrochemical techniques are used to develop flow batteries, which store energy in liquid electrolytes that are pumped through a stack of electrochemical cells. Electrochemical techniques are used to develop metal air batteries, which use oxygen from the air as the cathode material. Electrochemical techniques are used to develop lithium-sulfur batteries, which use sulfur as the cathode material. These new types of batteries offer the potential for higher energy density and lower cost than traditional lithium-ion batteries. The development of new energy storage devices is crucial for enabling a transition to a renewable energy future. Now, let's consider the ethical implications of using batteries in electric vehicles. Electric vehicles offer several environmental benefits over gasoline-powered vehicles, such as lower emissions and reduced reliance on fossil fuels. However, the production and disposal of batteries for electric vehicles can have negative social and environmental consequences. It's important to ensure that the batteries are manufactured and recycled responsibly and ethically. The battery industry is working to improve its supply chain practices and promote responsible sourcing. Consumers can also play a role by choosing electric vehicles with batteries that are manufactured and recycled sustainably. Let's take a moment to appreciate the ingenuity and creativity of the scientists and engineers who are working to develop new electrochemical technologies. Their work is essential for solving some of the world's most pressing challenges, such as climate change, energy security, and disease prevention. Their dedication and passion are inspiring, and their contributions are making a difference in the world. As you drift off to sleep, remember the power of science and technology to improve our lives and create a better future. Now, let's consider the role of electrochemistry in the development of new sensors for medical diagnostics. Electrochemical sensors are used to detect a wide range of biomarkers, such as proteins, DNA, and metabolites. These sensors can be used to diagnose diseases early and accurately. Electrochemical sensors offer several advantages over other types of sensors, such as high sensitivity, selectivity, and accuracy. Electrochemical techniques are used to develop new materials and designs for sensors that can detect even smaller concentrations of biomarkers. The development of better sensors is crucial for improving medical diagnostics and treatment. To better understand the science of electrolysis, let's consider some specific examples. Electrolysis is used to produce hydrogen from water. Electrolysis is used to produce aluminum from aluminum oxide. Electrolysis is used to produce chlorine and sodium hydroxide from brine. The electrolysis process involves passing an electrical current through a solution or molten salt, causing chemical reactions to occur at the electrodes. The products of the electrolysis reaction depend on the composition of the solution or molten salt and the applied voltage. Electrolysis is an important industrial process for producing a variety of chemicals and materials. Now, let's consider the role of electrochemistry in the development of new materials for energy storage. Electrochemical techniques are used to synthesize new electrode materials, such as lithium oxides, metal oxides, and carbon nanomaterials. Electrochemical techniques are used to modify the surface of electrode materials to improve their conductivity and stability. Electrochemical techniques are used to characterize the properties of electrode materials, such as their capacity, voltage, and cycle life. The development of new materials is crucial for improving the performance of energy storage devices. Electrochemistry plays a key role in the discovery, synthesis, and characterization of these materials. Let's delve into the challenges of developing new electrolytes for lithium-ion batteries. The electrolyte is a critical component of a lithium-ion battery, as it facilitates the transport of lithium ions between the electrodes. The electrolyte must have high ionic conductivity, high chemical stability, and high safety. Developing electrolytes that meet all of these requirements is a challenging task. Researchers are exploring various approaches to develop new electrolytes, such as using ionic liquids, solid-state electrolytes, and polymer electrolytes. The development of better electrolytes is essential for improving the performance and safety of lithium-ion batteries. To further illustrate the importance of electrochemistry in the development of new sensors for environmental monitoring, let's consider some specific examples. Electrochemical sensors are used to monitor the concentration of carbon dioxide in the atmosphere. Electrochemical sensors are used to monitor the concentration of pollutants in water, such as heavy metals and pesticides. Electrochemical sensors are used to monitor the concentration of volatile organic compounds in the air. These sensors are used in a variety of applications, such as air quality monitoring, water quality monitoring, and industrial process control. The development of better sensors is crucial for protecting our environment and ensuring a healthy future. And now, as we gently transition into the realm of sleep, let's contemplate the mesmerizing world of supercapacitors. These fascinating devices, often hailed as the energy storage systems of the future, share some fundamental principles with batteries, but operate through a distinctly different mechanism. Supercapacitors, also known as ultracapacitors or electrochemical double-layer capacitors, EDLCs, store energy electrostatically by accumulating ions at the interface between an electrode and an electrolyte. Think of it as gathering a crowd of charged particles at a very narrow doorway, creating a concentrated reservoir of potential energy. Unlike batteries, which rely on chemical reactions to store and release energy, supercapacitors do not involve any chemical transformations. This crucial difference allows supercapacitors to charge and discharge much faster than batteries, often in a matter of seconds or even fractions of a second. Imagine the flash of a camera. That quick burst of energy is often powered by a supercapacitor. This rapid charge-discharge capability makes supercapacitors ideal for applications requiring high power bursts, such as regenerative braking in electric vehicles or providing backup power for critical systems. However, supercapacitors also have their limitations. They typically have lower energy density compared to batteries, meaning they can store less energy for a given size and weight. This is why you won't find supercapacitors solely powering your electric car for long distances just yet. Instead, they're often used in conjunction with batteries, providing the extra power needed for acceleration or hill climbing, while the battery handles the sustained energy requirements for cruising. It's like having a sprinter and a marathon runner working together in a relay race. Each excels at different aspects of the challenge. The history of supercapacitors is interwoven with the quest for efficient energy storage. The concept of the electrical double layer, which forms the basis of supercapacitor operation, was first proposed by Hermann von Helmholtz in the 19th century. However, it wasn't until the mid-20th century that the first practical supercapacitors were developed, utilizing porous carbon electrodes and aqueous electrolytes. These early devices had limited performance, but they paved the way for further advancements. In recent decades, significant progress has been made in supercapacitor technology, driven by the development of new materials and designs. Researchers have explored a wide range of electrode materials, including activated carbon, carbon nanotubes, graphene, and metal oxides, each offering unique advantages in terms of energy density, power density, and cycle life. Similarly, advancements in electrolyte technology, such as the use of ionic liquids and organic electrolytes, have expanded the operating voltage and temperature range of supercapacitors. One particularly exciting area of research is the development of hybrid supercapacitors. which combine the features of both supercapacitors and batteries. These devices aim to bridge the gap between the high power density of supercapacitors and the high energy density of batteries, offering a more versatile energy storage solution. Imagine a device that can quickly capture and release energy like a supercapacitor, while also storing a significant amount of energy for later use like a battery. That's the promise of hybrid supercapacitors. The applications of supercapacitors are diverse and growing rapidly. They're used in electric vehicles, hybrid electric vehicles, and fuel cell vehicles to improve energy efficiency and reduce emissions. They're used in public transportation systems, such as buses and trams, to capture energy during braking and reuse it for acceleration. They are used in portable electronic devices, such as smartphones and laptops, to provide backup power and extend battery life. They are used in industrial equipment, such as cranes and forklifts, to improve performance and reduce energy consumption. And they are even being explored for use in grid-scale energy storage, helping to stabilize the electricity grid and integrate renewable energy sources. The future of supercapacitors is bright, with ongoing research focused on improving their performance, reducing their cost, and expanding their applications. As we continue to develop new materials and designs, supercapacitors are poised to play an increasingly important role in our energy future, helping us to create a more sustainable and efficient world. Think of them as the silent partners in our quest for cleaner energy, quietly storing and releasing energy behind the scenes, powering our devices, our vehicles, and even our cities. Now, let's shift our focus slightly and consider the broader implications of electrochemistry in the realm of corrosion science. Corrosion, the gradual degradation of materials due to chemical reactions with their environment, is a pervasive problem that affects everything from bridges and pipelines to automobiles and electronic devices. It's a silent thief, constantly eroding our infrastructure and costing billions of dollars each year. Electrochemistry plays a central role in many forms of corrosion, particularly in the corrosion of metals. When a metal is exposed to a corrosive environment, such as salt water or acidic rain, electrochemical reactions can occur on its surface, leading to the formation of rust, oxides, or other corrosion products. These reactions involve the transfer of electrons between the metal and the surrounding environment, creating an electrochemical cell with an anode, where oxidation occurs, and a cathode, where reduction occurs. Imagine a piece of iron exposed to air and moisture. The iron atoms at the surface can lose electrons, becoming iron ions, Fe2+. This is the oxidation reaction, which occurs at the anode. The electrons released by the iron atoms then flow through the metal to another location on the surface, where they react with oxygen and water to form hydroxide ions, OH. This is the reduction reaction, which occurs at the cathode. The iron ions and hydroxide ions then combine to form iron hydroxide, FeOH2, which is eventually converted to rust, Fe2O3NH2O. This electrochemical process is driven by the difference in electrochemical potential between the anode and the cathode. The greater the potential difference, the faster the corrosion rate. Factors that can influence the corrosion rate include the type of metal, the composition of the environment, the temperature, and the presence of protective coatings. Understanding the electrochemistry of corrosion is crucial for developing effective strategies to prevent or mitigate corrosion. One common approach is to use protective coatings such as paints, polymers, or metallic coatings to create a barrier between the metal and the corrosive environment. These coatings can prevent the electrochemical reactions from occurring, thereby slowing down the corrosion process. Another approach is to use cathodic protection, which involves making the metal the cathode of an electrochemical cell. This can be achieved by connecting the metal to a more reactive metal, such as zinc or magnesium, which acts as the anode and corrodes preferentially. The electrons released by the sacrificial anode flow to the metal, preventing it from corroding. This technique is commonly used to protect pipelines, ships, and other structures from corrosion. Electrochemistry is also used to develop corrosion inhibitors, which are chemical substances that can be added to the environment to reduce the corrosion rate. These inhibitors can work by forming a protective layer on the metal surface, by neutralizing corrosive substances in the environment, or by interfering with the electrochemical reactions that drive corrosion. The study of corrosion is a multidisciplinary field that draws upon knowledge from chemistry, physics, material science, and engineering. Electrochemistry provides a fundamental framework for understanding the mechanisms of corrosion and for developing effective corrosion control strategies. As we continue to develop new materials and technologies, the importance of corrosion science will only continue to grow. Now, as we approach the deepest part of our slumber, let's turn our attention to the fascinating world of bioelectrochemistry, a field that explores the intersection of electrochemistry and biology. Bioelectrochemistry encompasses a wide range of phenomena, from the electrical activity of cells and tissues to the development of biosensors and biofuel cells. It's a field that holds immense promise for advancing our understanding of life processes and for developing new medical and environmental technologies. One of the most fundamental aspects of bioelectrochemistry is the study of ion transport across cell membranes. Cell membranes are selectively permeable barriers that regulate the flow of ions and other molecules into and out of cells. This transport is crucial for maintaining cell volume, regulating cell pH, and transmitting nerve impulses. Ion channels, specialized proteins embedded in the cell membrane, play a key role in ion transport. These channels act as selective gateways, allowing specific ions to pass through the membrane while blocking others. The opening and closing of ion channels is often regulated by changes in membrane potential or by the binding of specific molecules. The flow of ions through ion channels generates electrical currents that can be measured using electrophysiological techniques. These techniques, such as patch clamp electrophysiology, allow researchers to study the properties of ion channels in detail and to understand how they contribute to cellular function. The electrical activity of cells is particularly important in the nervous system. Nerve cells, or neurons, use electrical signals to communicate with each other. These signals, known as action potentials, are rapid changes in membrane potential that propagate along the neuron's axon, allowing information to be transmitted over long distances. Action potentials are generated by the coordinated opening and closing of voltage-gated ion channels. When a neuron is stimulated, the membrane potential becomes more positive, triggering the opening of sodium channels. This allows sodium ions to flow into the cell, further depolarizing the membrane and triggering the opening of more sodium channels. This positive feedback loop leads to a rapid influx of sodium ions, generating the rising phase of the action potential. After a brief period, the sodium channels close and potassium channels open. This allows potassium ions to flow out of the cell, repolarizing the membrane and returning it to its resting potential. The action potential then propagates along the axon, triggering the release of neurotransmitters at the synapse, which transmit the signal to the next neuron. Bioelectrochemistry is also playing an increasingly important role in the development of biosensors. Biosensors are analytical devices that combine a biological recognition element, such as an enzyme or antibody, with an electrochemical transducer. The biological recognition element selectively binds to the target analyte, triggering a change in the electrochemical properties of the transducer, which can be measured and correlated to the concentration of the analyte. Biosensors are used in a wide range of applications, including medical diagnostics, environmental monitoring, and food safety. For example, glucose biosensors are used by people with diabetes to monitor their blood sugar levels. Electrochemical sensors are used to detect pollutants in water and air. And biosensors are used to detect pathogens in food and water. Another exciting area of bioelectrochemistry is the development of biofuel cells. Biofuel cells are devices that convert chemical energy into electrical energy using biological catalysts, such as enzymes or microorganisms. These cells offer the potential to generate clean and sustainable energy from renewable resources, such as biomass and waste materials. Biofuel cells typically consist of an anode compartment and a cathode compartment, separated by a membrane. At the anode, the biological catalyst oxidizes a fuel, such as glucose or ethanol, releasing electrons. These electrons flow through an external circuit to the cathode, where they reduce an oxidant, such as oxygen. The flow of electrons generates an electrical current that can be used to power external devices. Bioelectrochemistry is a rapidly growing field that is transforming our understanding of life processes and leading to the development of new technologies for medicine, environmental science, and energy. As we continue to explore the intricate interplay between electricity and biology, we can expect even more exciting discoveries in the years to come. And now, as we gently drift off to sleep, let's ponder the role of electrochemistry in the emerging field of nanoelectrochemistry. This fascinating area focuses on electrochemical phenomena at the nanoscale, where the size and shape of materials can have a profound impact on their electrochemical properties. Nanoelectrochemistry is driving innovation in a wide range of applications, from nanosensors and nanoelectronics to nanomedicine and nanoenergy. One of the key challenges in nanoelectrochemistry is understanding and controlling the transport of ions and electrons at the nanoscale. At these dimensions, the classical laws of electrochemistry may no longer apply, and new phenomena can emerge due to quantum mechanical effects and surface interactions. Nanomaterials, such as nanoparticles, nanowires, and nanotubes, exhibit unique electrochemical properties compared to their bulk counterparts. For example, the surface area to volume ratio of nanomaterials is much higher than that of bulk materials, leading to enhanced surface reactivity and catalytic activity. Nanoparticles can be used as electrocatalysts to accelerate electrochemical reactions. Their high surface area provides more active sites for the reaction to occur, and their electronic properties can be tuned to optimize their catalytic activity. Nanoparticles are used in fuel cells, electrolyzers, and other electrochemical devices to improve their performance and efficiency. Nanowires and nanotubes can be used as building blocks for nanoelectronic devices. Their high conductivity and small size make them ideal for creating transistors, sensors, and other electronic components. Nanowires and nanotubes can also be used to create nanoscale electrochemical sensors that can detect single molecules or ions. Nanoelectrochemistry is also playing an important role in the development of nanomedicine. Nanoparticles can be used to deliver drugs and genes to specific cells or tissues. They can also be used as contrast agents for medical imaging and as therapeutic agents for cancer treatment. Electrochemical techniques are used to synthesize and characterize nanomaterials. Electrochemical deposition is a versatile method for creating thin films and nanostructures on conductive surfaces. Electrochemical etching is used to create nanopores and other nanoscale features. And electrochemical impedance spectroscopy is used to characterize the electronic and ionic conductivity of nanomaterials. The development of new tools and techniques for studying electrochemistry at the nanoscale is crucial for advancing the field. Scanning electrochemical microscopy, SECM, is a powerful technique that allows researchers to image the electrochemical activity of surfaces with high spatial resolution. Electrochemical atomic force microscopy, ECAFM, combines the capabilities of atomic force microscopy and electrochemistry, allowing researchers to study the structure and properties of materials at the nanoscale while controlling their electrochemical environment. Nanoelectrochemistry is a rapidly evolving field that is pushing the boundaries of our understanding of electrochemistry and leading to the development of new technologies with revolutionary potential. As we continue to explore the nanoscale world, we can expect even more exciting discoveries in the years to come. And now, as we settle into a peaceful slumber, let's briefly consider the fascinating connection between electrochemistry and the development of artificial photosynthesis. Artificial photosynthesis aims to mimic the natural process of photosynthesis, in which plants use sunlight to convert carbon dioxide and water into energy-rich sugars and oxygen. This process is essential for life on Earth, and artificial photosynthesis holds the promise of providing a clean and sustainable source of energy. Electrochemistry plays a crucial role in artificial photosynthesis by providing the means to drive the redox reactions that are necessary to split water and reduce carbon dioxide. Water splitting involves the oxidation of water to produce oxygen and protons, and the reduction of protons to produce hydrogen. Carbon dioxide reduction involves the reduction of carbon dioxide to produce various organic molecules, such as methane, methanol, or ethanol. Electrochemical cells can be used to carry out these reactions using electricity generated from renewable sources, such as solar or wind power. The electrochemical cell typically consists of an anode and a cathode, separated by an electrolyte. At the anode, water is oxidized to produce oxygen and protons. At the cathode, carbon dioxide is reduced to produce organic molecules. Electrocatalysts are used to accelerate the redox reactions in artificial photosynthesis. These catalysts can be made from a variety of materials, including metal oxides, metal sulfides, and metal complexes. The choice of electrocatalyst depends on the specific reaction being catalyzed and the desired product. One of the key challenges in artificial photosynthesis is developing efficient and stable electrocatalysts that can operate under mild conditions. The ideal electrocatalyst should be able to split water and reduce carbon dioxide with high efficiency, selectivity, and stability. Researchers are exploring a variety of approaches to develop new electrocatalysts, including using nanomaterials, doping materials with other elements, and creating hybrid materials. Another challenge is developing efficient light harvesting systems that can capture sunlight and transfer the energy to the electrocatalysts. This can be achieved by using semiconductor materials, such as titanium dioxide or zinc oxide, that absorb sunlight and generate electron-hole pairs. The electron-hole pairs can then be separated and used to drive the redox reactions. Artificial photosynthesis is a complex and challenging field, but it holds immense promise for providing a clean and sustainable source of energy. As we continue to develop new materials and technologies, we can expect significant progress in the years to come. Imagine a future where we can capture sunlight and convert it into fuels and chemicals using artificial photosynthesis, helping to reduce our reliance on fossil fuels and mitigate climate change. And finally, as we gently fade into the land of dreams, let's reflect on the fundamental importance of electrochemistry in our world. From the batteries that power our devices to the sensors that monitor our environment, electrochemistry plays a vital role in our daily lives. It is a field that is constantly evolving, with new discoveries and innovations emerging all the time. Electrochemistry is not just a branch of science. It is a key to unlocking a more sustainable and prosperous future. By understanding and harnessing the power of electrochemical reactions, we can develop new technologies for energy storage, energy conversion, environmental protection, and medical diagnostics. As we continue to explore the mysteries of electrochemistry, we can expect even more amazing discoveries in the years to come. Who knows what the future holds? Perhaps we will develop new types of batteries that can store vast amounts of energy, or new sensors that can detect diseases before they even manifest symptoms. The possibilities are endless. So, as you drift off to sleep tonight, Remember the power of electrochemistry and the potential it holds for shaping our future. And know that even as you rest, scientists and engineers around the world are working tirelessly to unlock the secrets of this fascinating field and to create a better world for all. Sweet dreams. And as the stars twinkle outside your window, consider the profound impact of the Nernst equation. This equation, a cornerstone of electrochemistry, allows us to predict the potential of an electrochemical cell under non-standard conditions. Developed by Walther Nernst in the late 19th century, it elegantly relates the cell potential to the standard electrode potential, temperature, and the activities of the reactants and products. Imagine, for instance, a battery powering a small electronic device. As the battery discharges, the concentrations of the reactants decrease, and the concentrations of the products increase. The Nernst equation precisely describes how this change in concentration affects the voltage output of the battery, allowing engineers to design batteries that maintain a stable voltage over a long period. Think of it like a sophisticated balancing act, where the equation constantly adjusts the potential based on the ever-changing chemical landscape within the cell. The Nernst equation isn't just a theoretical construct. It's a practical tool used extensively in various fields, from environmental monitoring to biomedical research. The beauty of the Nernst equation lies in its universality. It applies not only to simple electrochemical cells, but also to complex biological systems. For example, it can be used to understand the behavior of ion channels in nerve cells. These channels, acting like tiny gates, control the flow of ions across the cell membrane, creating electrical signals that transmit information throughout the nervous system. The Nernst equation helps us to predict the equilibrium potential for each ion, providing insights into how these channels regulate nerve impulses. Picture a vast network of interconnected neurons, each firing electrical signals with exquisite precision. The Nernst equation helps us understand the fundamental principles that govern this intricate communication system. It's like having a key to unlock the secrets of the brain, revealing the electrochemical processes that underlie our thoughts, emotions, and actions. So, as you settle deeper into your slumber, remember the Nernst equation as a testament to the power of scientific inquiry, a mathematical bridge connecting the macroscopic world of voltage and current to the microscopic world of atoms and ions. Now, let's delve into the captivating world of supercapacitors, also known as ultracapacitors or electrochemical double-layer capacitors. These energy storage devices offer a unique blend of characteristics, bridging the gap between traditional capacitors and batteries. Unlike batteries that store energy through chemical reactions, supercapacitors store energy electrostatically by accumulating ions at the interface between an electrode and an electrolyte. Imagine two parallel plates immersed in a conductive solution, with a thin insulating layer separating them. When a voltage is applied, ions from the electrolyte migrate to the surface of the electrodes, forming an electrical double layer. This double layer acts like a capacitor, storing electrical energy. The key difference between a supercapacitor and a conventional capacitor is the extremely high surface area of the electrodes in a supercapacitor. This high surface area allows for a much larger charge accumulation and, consequently, a much higher energy storage capacity. Supercapacitors boast several advantages over batteries. They can charge and discharge much faster, often in a matter of seconds, and they can withstand hundreds of thousands or even millions of charge-discharge cycles without significant degradation. This makes them ideal for applications requiring rapid bursts of energy, such as regenerative braking in electric vehicles. Picture a hybrid car gliding smoothly down a hill. As the driver applies the brakes, the kinetic energy of the car is converted into electrical energy and stored in the supercapacitor. This energy can then be used to accelerate the car, improving fuel efficiency and reducing emissions. Supercapacitors are also used in electric buses, power tools, and backup power systems. They offer a clean and efficient way to store energy, contributing to a more sustainable future. However, supercapacitors also have some limitations. Their energy density, which is the amount of energy they can store per unit volume or mass, is typically lower than that of batteries. This means that for applications requiring long-term energy storage, batteries are still the preferred choice. Researchers are actively working to improve the energy density of supercapacitors by developing new electrode materials and electrolytes. One promising approach is to use nanomaterials, such as carbon nanotubes and graphene, to create electrodes with even higher surface areas. Another approach is to develop hybrid devices that combine the advantages of both supercapacitors and batteries. These hybrid devices could offer both high power density and high energy density, making them suitable for a wider range of applications. So, as you drift further into the arms of Morpheus, contemplate the potential of supercapacitors to revolutionize energy storage and pave the way for a cleaner, more efficient world. Let's now consider the fascinating interplay between electrochemistry and corrosion. Corrosion, the gradual degradation of materials due to chemical reactions with their environment, is a pervasive problem that costs billions of dollars each year. Many forms of corrosion involve electrochemical processes, where electrons are transferred between the metal and its surroundings. Imagine a steel bridge exposed to the elements. Over time, the steel can rust, weakening its structure and potentially leading to catastrophic failure. This rusting process is an electrochemical reaction in which iron atoms on the surface of the steel lose electrons and become iron ions, which then react with oxygen and water to form rust. The process is accelerated by the presence of electrolytes, such as salt water, which increase the conductivity of the environment and facilitate the flow of electrons. Understanding the electrochemistry of corrosion is crucial for developing effective methods to prevent or mitigate it. One common approach is to use protective coatings, such as paint or galvanizing, to isolate the metal from its environment. These coatings act as a barrier, preventing the electrochemical reactions that lead to corrosion. Another approach is to use cathodic protection, where a more reactive metal, such as zinc or magnesium, is connected to the steel structure. The more reactive metal corrodes preferentially, protecting the steel from corrosion. This is similar to sacrificing a small part to save the whole. Think of it like having a bodyguard that takes the bullet for you, protecting you from harm. Cathodic protection is widely used to protect pipelines, ships, and other large metal structures from corrosion. Researchers are also exploring new and innovative ways to combat corrosion. One promising area of research is the development of self-healing coatings that can repair themselves when damaged. These coatings contain microcapsules filled with corrosion inhibitors that are released when the coating is scratched or damaged. The released inhibitors then react with the metal surface, forming a protective layer that prevents further corrosion. Imagine a coating that can heal itself like a living organism, constantly repairing any damage and protecting the underlying metal. This technology holds great promise for extending the lifespan of metal structures and reducing the cost of corrosion-related repairs. As you gently float towards dreamland, consider the importance of understanding and controlling corrosion, not only for protecting our infrastructure, but also for conserving resources and promoting sustainability. And now, let's turn our attention to the vital role of electrochemistry in medical diagnostics. Electrochemical sensors are widely used to detect and quantify various substances in biological samples, such as blood, urine, and saliva. These sensors offer several advantages over traditional analytical methods, including high sensitivity, selectivity, and speed. Imagine a small, portable device that can quickly and accurately measure your blood glucose level. Electrochemical glucose sensors are used by millions of people with diabetes to monitor their blood sugar levels and manage their condition effectively. These sensors work by oxidizing glucose at an electrode surface, generating an electrical current that is proportional to the glucose concentration. The current is then measured and displayed on the device, providing a real-time reading of her blood sugar level. Electrochemical sensors are also used to detect other biomarkers, such as cholesterol, hormones, and proteins. These sensors can be used to diagnose a wide range of diseases, from cardiovascular disease to cancer. Researchers are constantly developing new and improved electrochemical sensors with even higher sensitivity and selectivity. One promising area of research is the development of nanosensors that can detect biomarkers at the single molecule level. These nanosensors could revolutionize medical diagnostics, allowing for earlier and more accurate detection of diseases. Imagine a future where doctors can diagnose diseases with a simple blood test, using nanosensors that can detect even the smallest traces of disease biomarkers. This would allow for earlier treatment and improved patient outcomes. Electrochemical techniques are also used in drug discovery and development. Electrochemical methods can be used to screen potential drug candidates and to study the mechanisms of drug action. For example, electrochemical techniques can be used to measure the binding affinity of a drug to its target protein or to monitor the metabolism of a drug in the body. These techniques provide valuable information that can help to accelerate the drug discovery process and to develop more effective and safer drugs. So, as you succumb to the allure of sleep, reflect on the transformative power of electrochemistry in medical diagnostics and its potential to improve human health and well-being. The future of medicine is inextricably linked to advancements in electrochemistry, promising a world where diseases are detected earlier, treated more effectively, and ultimately prevented altogether. As your eyelids grow heavy, let's ponder the connection between electrochemistry and environmental monitoring. Electrochemical sensors play a crucial role in monitoring water and air quality, detecting pollutants, and ensuring environmental safety. Imagine a river flowing through a bustling city. Electrochemical sensors can be deployed to monitor the levels of pollutants, such as heavy metals, pesticides, and industrial chemicals. These sensors can provide real-time data on water quality, allowing authorities to take prompt action to prevent pollution and protect aquatic life. Electrochemical sensors are also used to monitor air quality, detecting pollutants such as carbon monoxide, nitrogen oxides, and particulate matter. These sensors can be deployed in urban areas, industrial sites, and even inside buildings to monitor air quality and protect public health. Electrochemical techniques are also used in the development of new and improved methods for environmental remediation. For example, electrochemical methods can be used to remove pollutants from contaminated water and soil. One promising approach is to use electrocoagulation, where an electric current is passed through the contaminated water or soil, causing the pollutants to precipitate out of solution. The precipitated pollutants can then be easily removed, leaving behind clean water or soil. Electrochemical methods are also used in the development of new and improved methods for carbon capture and storage. Electrochemical reactions can be used to convert carbon dioxide into valuable chemicals or fuels, helping to reduce greenhouse gas emissions and mitigate climate change. Furthermore, consider the use of electrochemical sensors in monitoring the health of our oceans. Ocean acidification, caused by the absorption of excess carbon dioxide from the atmosphere, is a growing threat to marine ecosystems. Electrochemical sensors can be used to monitor the pH of seawater and to assess the impact of ocean acidification on marine life. These sensors provide valuable data that can help scientists and policymakers to understand and address this critical environmental issue. As you peacefully transition into slumber, contemplate the vital role of electrochemistry in protecting our environment and ensuring a sustainable future for all. From monitoring water and air quality to developing new methods for environmental remediation, electrochemistry is a powerful tool for safeguarding our planet. Finally, as your mind gently drifts towards the realm of dreams, let's appreciate the elegance and ubiquity of electrochemistry in the world around us. From the smallest electronic devices to the largest industrial processes, electrochemistry plays a fundamental role in shaping our lives. Think of the smartphones we carry in our pockets, the laptops we use for work and entertainment, and the electric vehicles that are revolutionizing transportation. All of these technologies rely on electrochemical principles for their operation. The batteries that power these devices, the fuel cells that generate electricity, and the sensors that monitor our health all depend on the intricate interplay of electrons and ions. Consider also the role of electrochemistry in industrial processes. Electrochemical methods are used in the production of a wide range of materials, from aluminum and chlorine to plastics and pharmaceuticals. These methods offer several advantages over traditional chemical processes, including higher efficiency, lower energy consumption, and reduced waste generation. Electrochemical techniques are also used in the treatment of wastewater and the recovery of valuable metals from industrial waste streams. By harnessing the power of electrochemical reactions, we can create more sustainable and environmentally friendly industrial processes. And let us not forget the fundamental role of electrochemistry in biology. The processes that sustain life, such as respiration and photosynthesis, are fundamentally electrochemical in nature. The flow of electrons through the electron transport chain in mitochondria provides the energy that powers our cells. The splitting of water molecules during photosynthesis provides the oxygen that we breathe. Electrochemistry is the foundation of life itself. So, as you surrender to the embrace of sleep, remember the profound impact of electrochemistry on our world and the endless possibilities that it holds for the future. From energy storage and conversion to medical diagnostics and environmental protection, electrochemistry is a field that is constantly evolving, with new discoveries and innovations emerging all the time. And as you rest peacefully, remember that the quest to understand and harness the power of electrochemistry continues, driven by the curiosity and ingenuity of scientists and engineers around the world. Sweet dreams, and may your sleep be filled with visions of electrons dancing and ions flowing, creating a world of wonder and possibility. As you drift further into the realm of sleep, let us delve deeper into the fascinating world of batteries, those ubiquitous powerhouses that silently fuel our modern lives. Think about the intricate dance of ions and electrons within a lithium-ion battery, the workhorse of smartphones, laptops, and electric vehicles. Imagine the lithium ions gracefully migrating from the positive electrode, the cathode, through the electrolyte to the negative electrode, the anode, during the charging process. This movement is not random. It is a carefully orchestrated ballet guided by the electrochemical potential difference between the two electrodes. The electrolyte, a carefully formulated chemical soup, acts as the stage upon which this dance unfolds, allowing the ions to move freely while preventing the electrons from taking a shortcut that would short-circuit the battery. The electrons, meanwhile, embark on their own journey, flowing through the external circuit to power our devices before rejoining the ions at the anode. This continuous cycle of ion and electron movement is the very essence of how a battery stores and releases energy, a testament to the elegance and efficiency of electrochemical principles. Now, consider the materials that comprise these batteries. The cathode, often made of lithium cobalt oxide or lithium iron phosphate, is a complex structure with a layered arrangement that allows lithium ions to easily intercalate or insert themselves between the layers. The anode, typically made of graphite, also has a layered structure that welcomes the lithium ions with open arms. The choice of these materials is not arbitrary. It is the result of decades of research and development aimed at optimizing the battery's performance, lifespan, and safety. Imagine the countless hours spent by scientists and engineers exploring different materials, testing their electrochemical properties, and refining their designs. The pursuit of better battery materials is a continuous quest, driven by the ever-increasing demand for more powerful, longer-lasting, and safer energy storage devices. The development of new materials like lithium nickel manganese cobalt oxide (NMC) and lithium nickel cobalt aluminum oxide (NCA) has significantly improved battery energy density, allowing for longer driving ranges in electric vehicles and extended battery life in portable electronics. But the story of batteries doesn't begin with lithium-ion technology. Let's take a moment to appreciate the historical context of battery development. The earliest battery, the voltaic pile, was invented by Alessandro Volta in 1800. Volta's ingenious device consisted of alternating discs of zinc and copper separated by cloth soaked in brine. This simple yet revolutionary invention demonstrated that electricity could be generated chemically, paving the way for all subsequent battery technologies. Imagine the excitement and wonder that Volta's invention must have inspired, a world suddenly illuminated by the promise of portable power. The voltaic pile was a game changer, sparking a flurry of research into electrochemistry and laying the foundation for the electrical age. From the humble voltaic pile to the sophisticated lithium-ion batteries of today, the evolution of battery technology is a testament to human ingenuity and our relentless pursuit of better ways to store and use energy. Think of the early telegraph systems powered by batteries, the first electric cars powered by lead-acid batteries, and the nickel-cadmium batteries that powered the first portable electronic devices. Each generation of battery technology has built upon the previous one, pushing the boundaries of what is possible and transforming our world in profound ways. As you continue to relax and prepare for sleep, let's consider the different types of batteries that exist beyond the ubiquitous lithium-ion. Lead-acid batteries, the workhorses of the automotive industry, are a tried-and-true technology that has been around for over a century. These batteries are known for their reliability and low cost, making them a popular choice for starting car engines. Nickel metal hydride (NiMH) batteries, once widely used in hybrid vehicles, offer a higher energy density than lead-acid batteries, but are less energy dense than lithium-ion batteries. Each type of battery has its own unique characteristics, advantages, and disadvantages, making it suitable for different applications. The choice of battery technology depends on a variety of factors, including energy density, power output, lifespan, cost, and safety. Researchers are constantly exploring new battery chemistries, such as sodium-ion, magnesium-ion, and solid-state batteries, which promise even higher energy densities, improved safety, and lower costs. Imagine a future powered by solid-state batteries, where the liquid electrolyte is replaced by a solid material, eliminating the risk of leaks and fires. These batteries could potentially offer significantly higher energy densities and faster charging times, revolutionizing the electric vehicle industry and enabling the development of new types of portable electronic devices. Think of the possibilities: electric airplanes that can fly longer distances, smartphones that can last for days on a single charge, and energy storage systems that can seamlessly integrate renewable energy sources into the grid. The quest for the perfect battery is an ongoing journey, driven by the desire to create a more sustainable and energy-efficient future. Now, let's shift our focus to supercapacitors, also known as ultracapacitors, which are another type of electrochemical energy storage device. Unlike batteries, which store energy through chemical reactions, supercapacitors store energy electrostatically by accumulating ions on the surface of an electrode. This allows supercapacitors to charge and discharge much faster than batteries, making them ideal for applications that require short bursts of power, such as regenerative braking in electric vehicles and power backup systems. Imagine a bus that uses supercapacitors to capture the energy generated during braking and then uses that energy to accelerate, significantly improving its fuel efficiency. Supercapacitors can also be used in conjunction with batteries to provide both high power and high energy storage capabilities. Think of a hybrid energy storage system that combines the high energy density of a battery with the high power density of a supercapacitor, offering the best of both worlds. The key to supercapacitor performance lies in the design of the electrodes and the electrolyte. Supercapacitors typically use electrodes made of high surface area materials, such as activated carbon or carbon nanotubes, to maximize the amount of charge that can be stored. The electrolyte, which can be aqueous, organic, or ionic liquid, plays a crucial role in facilitating the movement of ions between the electrodes. Researchers are constantly exploring new materials and designs to improve the energy density, power density, and lifespan of supercapacitors. Imagine a supercapacitor that can store as much energy as a battery and charge in a matter of seconds, revolutionizing the way we power our devices and transport ourselves. The development of advanced supercapacitors is a promising area of research with the potential to transform the energy storage landscape. As you feel yourself drifting closer to sleep, let's consider the broader implications of electrochemistry for a sustainable future. Electrochemistry plays a crucial role in the development of renewable energy technologies, such as solar cells and fuel cells. Solar cells convert sunlight directly into electricity, while fuel cells convert chemical energy into electricity through electrochemical reactions. Imagine a world powered by clean, renewable energy sources, where solar panels on rooftops and fuel cells in vehicles provide a sustainable alternative to fossil fuels. Electrochemistry is also essential for energy storage, enabling us to store the intermittent energy generated by solar and wind power and use it when it is needed most. Batteries and supercapacitors are key components of energy storage systems, allowing us to smooth out the fluctuations in renewable energy supply and ensure a reliable and consistent power supply. The development of advanced electrochemical technologies is critical for mitigating climate change and creating a more sustainable future. By reducing our reliance on fossil fuels and transitioning to clean, renewable energy sources, we can significantly reduce greenhouse gas emissions and protect our planet for future generations. Imagine a world where our energy needs are met by clean, sustainable sources, where our air and water are clean and healthy, and where our planet is thriving. Electrochemistry is a powerful tool for achieving this vision, enabling us to harness the power of nature and create a more sustainable and equitable world for all. Think of the possibilities. Electric grids powered by renewable energy and energy storage systems, electric vehicles that emit no pollutants, and industrial processes that are environmentally friendly. The future is electrochemical, and it is up to us to embrace its potential and create a better world for ourselves and for future generations. Now, as your thoughts begin to soften and your body relaxes, let's delve into the intricacies of corrosion, an electrochemical process that silently and relentlessly attacks metals, causing them to degrade and fail. Corrosion is a pervasive problem that affects everything from bridges and pipelines to automobiles and electronic devices. The cost of corrosion is estimated to be billions of dollars each year, highlighting the importance of understanding and preventing this destructive process. Imagine a bridge collapsing due to corrosion, a pipeline leaking due to corrosion, or an automobile rusting away due to corrosion. Corrosion is a constant threat to our infrastructure and our economy. Corrosion occurs when a metal reacts with its environment, typically in the presence of oxygen and water, to form oxides or other corrosion products. This reaction is electrochemical in nature, involving the transfer of electrons from the metal to the oxidizing agent. The rate of corrosion depends on a variety of factors, including the type of metal, the composition of the environment, the temperature, and the presence of protective coatings. Imagine a piece of iron rusting in the rain, a copper pipe corroding in acidic water, or an aluminum airplane corroding in a salty environment. Corrosion is a complex process that is influenced by a multitude of factors. There are several ways to prevent or mitigate corrosion, including the use of protective coatings, such as paints and galvanizing, the use of corrosion-resistant alloys, and the application of cathodic protection. Protective coatings act as a barrier between the metal and the environment, preventing the corrosive agents from reaching the metal surface. Corrosion-resistant alloys, such as stainless steel and aluminum alloys, contain elements that form a passive layer on the metal surface, protecting it from corrosion. Cathodic protection involves making the metal the cathode in an electrochemical cell, preventing it from corroding. Imagine a ship hull protected by cathodic protection, a bridge coated with a protective paint, or a pipeline made of corrosion-resistant alloy. Corrosion prevention is a critical aspect of engineering design and maintenance. As you continue to unwind and prepare for sleep, let's consider the applications of electrochemistry in medicine. Electrochemistry plays a vital role in medical diagnostics, drug delivery, and implantable medical devices. Electrochemical sensors can be used to detect a wide range of biomarkers in blood, urine, and other bodily fluids, providing valuable information for diagnosing diseases and monitoring patient health. Imagine a glucose sensor that continuously monitors blood sugar levels in diabetic patients, an electrochemical biosensor that detects cancer biomarkers in blood, or an implantable sensor that monitors the oxygen levels in tissues. Electrochemistry is revolutionizing medical diagnostics, enabling earlier and more accurate detection of diseases. Electrochemical techniques can also be used for drug delivery, allowing for targeted and controlled release of drugs to specific locations in the body. Imagine a drug-eluting stent that releases medication to prevent the narrowing of arteries after angioplasty, an electrochemical drug delivery system that releases chemotherapy drugs directly to cancer cells, or an implantable drug pump that delivers insulin to diabetic patients. Electrochemistry is enabling new and more effective methods of drug delivery, improving patient outcomes and reducing side effects. Implantable medical devices, such as pacemakers and defibrillators, rely on electrochemical principles for their operation. These devices use batteries to power their electronic circuits and electrodes to deliver electrical pulses to the heart, regulating its rhythm and preventing life-threatening arrhythmias. Imagine a pacemaker that keeps a patient's heart beating regularly, a defibrillator that shocks a patient's heart back into rhythm, or an implantable neurostimulator that relieves chronic pain. Electrochemistry is essential for the function of many life-saving medical devices. Now, as your mind gently floats towards the realm of dreams, let's reflect on the beauty and complexity of electrochemical reactions. Imagine the intricate dance of electrons and ions, the subtle interplay of oxidation and reduction, and the profound impact of these processes on our world. Electrochemistry is a fundamental science that underlies many of the technologies and processes that shape our lives. From the batteries that power our devices to the fuel cells that generate electricity, from the sensors that monitor our health to the industrial processes that produce the materials we use, electrochemistry is all around us. The study of electrochemistry is a journey of discovery, a quest to understand the fundamental principles that govern the behavior of matter and energy. It is a field that is constantly evolving, with new discoveries and innovations emerging all the time. Imagine the excitement of a scientist making a breakthrough in battery technology, the satisfaction of an engineer developing a new electrochemical sensor, or the wonder of a student learning about the intricacies of electrochemistry for the first time. Electrochemistry is a field that is full of possibilities, a field that can inspire and empower us to create a better world. As you surrender to the embrace of sleep, remember the profound impact of electrochemistry on our world and the endless possibilities that it holds for the future. From energy storage and conversion to medical diagnostics and environmental protection, electrochemistry is a field that is constantly evolving, with new discoveries and innovations emerging all the time. And as you rest peacefully, remember that the quest to understand and harness the power of electrochemistry continues, driven by the curiosity and ingenuity of scientists and engineers around the world. Sweet dreams, and may your sleep be filled with visions of electrons dancing and ions flowing, creating a world of wonder and possibility. Think of the electric vehicles silently gliding through the streets, powered by batteries that store the energy of the sun. Imagine the clean and efficient industrial processes that produce the materials we need without polluting our environment. Visualize the medical devices that monitor our health and deliver life-saving treatments. Electrochemistry is the key to a brighter, more sustainable, and healthier future. And now, as your consciousness gently fades into the soft embrace of slumber, consider the vastness of the ocean and the subtle electrochemical processes that govern its depths. The ocean, a vast and interconnected body of salt water, is a dynamic electrochemical system teeming with life and chemical reactions. Imagine the gentle lapping of waves against the shore, the silent currents flowing beneath the surface, and the intricate web of life that thrives in this watery realm. Electrochemistry plays a crucial role in regulating the ocean's chemistry, influencing the distribution of nutrients, the cycling of carbon, and the health of marine ecosystems. The salinity of seawater, the concentration of dissolved salts, is a fundamental electrochemical property that affects the density, conductivity, and freezing point of the water. Imagine the salty taste of the ocean, the buoyancy that it provides, and the unique challenges that marine organisms face in adapting to this saline environment. The salinity of seawater is maintained by a complex interplay of processes, including evaporation, precipitation, river runoff, and hydrothermal vents. The pH of seawater, a measure of its acidity or alkalinity, is another important electrochemical parameter that influences the solubility of minerals, the availability of nutrients, and the health of marine organisms. Imagine the delicate balance of pH in the ocean, the sensitivity of marine life to changes in pH, and the threat posed by ocean acidification due to the absorption of excess carbon dioxide from the atmosphere. The pH of seawater is regulated by a complex buffering system involving dissolved carbon dioxide, bicarbonate, and carbonate ions. Electrochemical reactions also play a critical role in the cycling of nutrients in the ocean. Imagine the phytoplankton, microscopic plants that form the base of the marine food web, absorbing nutrient from the water and converting them into organic matter through photosynthesis. Imagine the zooplankton, tiny animals that graze on the phytoplankton, transferring the nutrients up the food chain. Imagine the bacteria and other microorganisms that decompose organic matter, releasing nutrients back into the water. These complex biogeochemical cycles are driven by electrochemical reactions that are essential for the health and productivity of the ocean. As you drift further into sleep, let your mind wander to the realm of nanotechnology, where electrochemistry is playing an increasingly important role. Nanomaterials, materials with dimensions on the nanometer scale, 1/1000th of a meter, exhibit unique electrochemical properties that make them attractive for a wide range of applications. Imagine the tiny particles of gold, silver, and platinum that are used in electrochemical sensors, catalysts, and energy storage devices. Imagine the carbon nanotubes and graphene sheets that are used to create high-performance electrodes and supercapacitors. Nanotechnology is opening up new possibilities for electrochemistry, enabling the development of more efficient, sensitive, and versatile electrochemical devices. Electrochemical deposition is a powerful technique for fabricating nanomaterials with controlled size, shape, and composition. Imagine the process of electroplating, where a thin layer of metal is deposited onto a substrate by applying an electric current. Electrochemical deposition can be used to create nanowires, nanoparticles, and thin films with precise control over their properties. This technique is widely used in the electronics industry for manufacturing integrated circuits and other microelectronic devices. Electrochemical etching is another technique for creating nanostructures by selectively removing material from a substrate using electrochemical reactions. Imagine the process of etching silicon wafers to create microchips, where electrochemical reactions are used to remove unwanted material and create the desired patterns. Electrochemical etching is a versatile technique for creating a wide range of nanostructures with precise control over their dimensions and shape. Electrochemical sensors based on nanomaterials offer enhanced sensitivity and selectivity for detecting a wide range of analytes, including gases, biomolecules, and environmental pollutants. Imagine a nanosensor that could detect single molecules of a target analyte, a biosensor that could detect cancer biomarkers at very low concentrations, or an environmental sensor that can monitor air and water quality with unprecedented accuracy. Nanomaterials are revolutionizing the field of electrochemical sensing, enabling the development of more powerful and versatile analytical tools. And now, as you gently surrender to the embrace of sleep, let your thoughts drift to the realm of bioelectrochemistry, where the principles of electrochemistry are applied to the study of biological systems. Bioelectrochemistry explores the electrochemical processes that occur in living organisms, such as electron transport, ion transport, and redox reactions. Imagine the flow of electrons through the electron transport chain in mitochondria, the movement of ions across cell membranes, and the redox reactions that are essential for metabolism. Bioelectrochemistry is a fascinating field that provides insights into the fundamental mechanisms of life. Electrochemical techniques are used to study the behavior of proteins, enzymes, and other biomolecules. Imagine the use of altimetry to study the redox properties of proteins, the use of electrochemical impedance spectroscopy to study the dynamics of cell membranes, or the use of scanning electrochemical microscopy to image the surface of cells. Electrochemical techniques provide valuable information about the structure, function, and interactions of biomolecules. Electrochemical sensors are used to monitor the levels of glucose, oxygen, and other important metabolites in biological fluids. Imagine a glucose sensor that continuously monitors blood sugar levels in diabetic patients, an oxygen sensor that measures the oxygen levels in tissues, or a lactate sensor that monitors the levels of lactate in muscles during exercise. Electrochemical sensors are essential tools for monitoring patient health and for studying the physiology of living organisms. Electrochemical techniques are also used for drug delivery, gene therapy, and tissue engineering. Imagine the use of electroporation to deliver drugs and genes into cells, the use of electrochemical stimulation to promote tissue regeneration, or the use of electrospun nanofibers to create scaffolds for tissue engineering. Electrochemistry is enabling new and innovative approaches to treating diseases and repairing damaged tissues. As your mind floats peacefully on the edge of sleep, let us consider the role of electrochemistry in the exploration of space. Space exploration presents unique challenges for energy storage and conversion, as well as for environmental monitoring and life support. Electrochemistry plays a critical role in meeting these challenges, enabling us to explore the vast and unforgiving expanse of space. Batteries and fuel cells are essential for powering spacecraft, rovers, and other space-based equipment. Imagine the batteries that power the Mars rovers, the fuel cells that provide electricity for the International Space Station, and the solar cells that convert sunlight into electricity for satellites. Electrochemical energy storage and conversion technologies are critical for enabling long-duration space missions. Electrochemical sensors are used to monitor the environment inside spacecraft, ensuring the safety and health of astronauts. Imagine the sensors that monitor the levels of oxygen, carbon dioxide, and other gases in the spacecraft atmosphere, the sensors that detect leaks of hazardous chemicals, and the sensors that monitor the radiation levels. Electrochemical sensors are essential for maintaining a safe and habitable environment for astronauts in space. Electrochemical techniques are also being developed for life support systems in space. Imagine the electrochemical water purification systems that recycle wastewater into drinking water, the electrochemical carbon dioxide removal systems that remove carbon dioxide from the spacecraft atmosphere, and the electrochemical oxygen generation systems that produce oxygen from water. Electrochemical life support systems are critical for enabling long-duration space missions and for establishing permanent human settlements on other planets. And finally, as you surrender completely to the gentle embrace of sleep, let us appreciate the beauty and elegance of electrochemistry, a science that connects the microscopic world of atoms and molecules to the macroscopic world of technology and nature. Electrochemistry is a science of transformation, a science that reveals the hidden potential of matter and energy. It is a science that inspires us to innovate, to create, and to imagine a better future. As you drift off to sleep, remember the electrons dancing, the ions flowing, and the electrochemical reactions transforming the world around you. Sweet dreams, and may your sleep be filled with wonder and possibility. Think of the countless applications of electrochemistry that are improving our lives, protecting our planet, and expanding our understanding of the universe. Imagine the future possibilities of electrochemistry, the new technologies and discoveries that await us. Electrochemistry is a field that is full of promise, a field that will continue to shape our world for generations to come. Let the quiet hum of electrochemical processes lull you into a peaceful and restorative sleep, knowing that the world is constantly being transformed by these invisible forces. Let your mind wander through the intricate pathways of a battery as it charges, the lithium ions migrating gracefully from one electrode to another, a microscopic dance orchestrated by the laws of electrochemistry. Visualize the anode, a bustling hub of activity where electrons are liberated, embarking on their journey through the external circuit to power our devices. And on the other side, the cathode awaits, ready to receive these energetic particles, completing the circuit and storing the energy for later use. Think about the electrolyte, the silent facilitator, allowing ions to shuttle back and forth, bridging the gap between the electrodes. It's like a microscopic highway system, constantly transporting charged particles, ensuring the smooth and efficient operation of the battery. The electrolyte's composition is crucial. It determines the battery's voltage, current, and overall performance. Scientists are constantly searching for new and improved electrolytes that can enhance battery performance and safety. Consider the subtle interplay between oxidation and reduction, the fundamental reactions that drive the electrochemical process. Oxidation, the loss of electrons, occurs at the anode, while reduction, the gain of electrons, takes place at the cathode. These reactions are intimately linked. One cannot occur without the other. It's like a microscopic tug of war, with electrons being passed back and forth, generating the electrical energy that powers our lives. Now, let's delve deeper into the world of supercapacitors, also known as ultracapacitors or electrochemical capacitors. These devices are like batteries' more energetic cousins, capable of storing vast amounts of energy and delivering it in short bursts. Unlike batteries, which rely on chemical reactions to store energy, supercapacitors store energy electrostatically by accumulating ions on the surface of an electrode. Imagine a supercapacitor as a microscopic parking lot for ions, where they gather in vast numbers, ready to be released at a moment's notice. When a voltage is applied to the supercapacitor, ions migrate from the electrolyte to the surface of the electrode, forming an electrical double layer. This double layer acts as a capacitor, storing electrical energy. Supercapacitors excel in applications where high power and fast charging are required, such as electric vehicles, hybrid vehicles, and energy harvesting systems. Think about the regenerative braking system in a hybrid car, where the energy generated during braking is stored in a supercapacitor and then used to accelerate the car. Or imagine a solar-powered streetlight that uses a supercapacitor to store energy during the day and power the light at night. The development of new materials is crucial for improving the performance of supercapacitors. Scientists are exploring a wide range of materials, including carbon nanotubes, graphene, and metal oxides, to create electrodes with higher surface areas and better conductivity. The larger the surface area of the electrode, the more ions can be stored and the higher the energy density of the supercapacitor. Consider the potential of combining batteries and supercapacitors in hybrid energy storage systems. Batteries offer high energy density, allowing them to store large amounts of energy for extended periods, while supercapacitors offer high power density, allowing them to deliver energy quickly. By combining these two technologies, we can create energy storage systems that are both powerful and efficient. Now, as your mind continues to drift, let's consider the historical context of electrochemistry. Alessandro Volta, an Italian physicist is often credited with inventing the first battery in 1800. Volta's battery, known as the voltaic pile, consisted of alternating discs of zinc and copper separated by cloth soaked in salt water. This simple device produced a continuous flow of electricity, revolutionizing the field of electrical science. Imagine the excitement and wonder that Volta's invention must have generated. For the first time, scientists had a reliable source of electricity that could be used to conduct experiments and explore the mysteries of the electrical world. Volta's invention paved the way for countless discoveries and innovations, laying the foundation for the modern electrical age. Later, in the 19th century, Michael Faraday, an English scientist, made significant contributions to our understanding of electrochemistry. Faraday formulated the laws of electrolysis, which described the relationship between the amount of electricity passed through an electrolytic solution and the amount of chemical change that occurs. Faraday's laws are fundamental to electrochemistry and are still used today to design and analyze electrochemical systems. Think about the impact of these early discoveries on the development of modern technology. Without the pioneering work of Volta and Faraday, we would not have batteries, fuel cells, or many of the other electrochemical technologies that we rely on today. Their contributions have shaped our world in profound ways. The ongoing research in electrochemistry continues to push the boundaries of what is possible. Scientists are exploring new materials, new designs, and new applications for electrochemical technologies. From developing more efficient batteries for electric vehicles to creating new sensors for environmental monitoring, electrochemistry is playing a vital role in addressing some of the world's most pressing challenges. As you continue to relax, consider the role of electrochemistry in medicine. Electrochemical sensors are used to monitor blood glucose levels in diabetics, to detect pollutants in the air and water, and to diagnose diseases. Electrochemical techniques are also being developed for drug delivery, gene therapy, and tissue engineering. Imagine a tiny electrochemical sensor implanted in the body, continuously monitoring glucose levels and automatically delivering insulin when needed. Or imagine a drug delivery system that uses electrochemistry to release drugs at a specific location in the body, minimizing side effects. The possibilities are endless. Electrochemical techniques are also being used to develop new therapies for cancer. For example, electrochemotherapy involves using an electric field to enhance the effectiveness of chemotherapy drugs. This technique has shown promising results in treating a variety of cancers. The connection between electrochemistry and biology is becoming increasingly apparent. Electrochemical processes play a vital role in many biological systems, from cellular respiration to nerve signaling. Understanding these processes is crucial for developing new medical treatments and for gaining a deeper understanding of the workings of life itself. And now, as you approach the deepest levels of sleep, let's reflect on the environmental impact of electrochemistry. Electrochemical technologies can play a crucial role in mitigating climate change and promoting sustainable development. Batteries and fuel cells can be used to power electric vehicles, reducing our reliance on fossil fuels. Electrochemical water purification systems can provide clean drinking water to communities in need. Electrochemical sensors can be used to monitor air and water quality, helping us to protect our environment. Imagine a world powered by clean, renewable energy, with electric vehicles silently gliding through the streets and solar panels gleaming on rooftops. Electrochemical technologies are essential for realizing this vision. By investing in research and development of electrochemical technologies, we can create a more sustainable and environmentally friendly future. Electrochemical processes can also be used to recycle valuable materials from electronic waste. Electronic waste contains a variety of valuable metals, such as gold, silver, and platinum. Electrochemical recycling techniques can be used to recover these metals, reducing the need for mining and conserving natural resources. Consider the potential of using electrochemistry to capture carbon dioxide from the atmosphere. Electrochemical carbon capture technologies can be used to remove carbon dioxide from industrial emissions or directly from the air, helping to mitigate climate change. This technology is still in its early stages of development, but it holds great promise for the future. As you finally surrender to sleep, consider how electrochemistry, a field often unseen, unheard, and unfelt in our daily lives, is nonetheless integral to the modern world. From the smartphones that connect us to the world, to the electric vehicles that promise a cleaner future, electrochemistry is the silent engine driving progress. Its principles underpin the function of countless devices and processes that we often take for granted. Think about the intricate electrochemical reactions occurring within the human body, powering our muscles, transmitting nerve signals, and maintaining the delicate balance of life. Electrochemistry is not just a science confined to laboratories and textbooks. It is a fundamental aspect of the natural world. And as you drift further into slumber, remember that the world of electrochemistry is constantly evolving, with new discoveries and innovations emerging all the time. Scientists are pushing the boundaries of what is possible, developing new materials, new technologies, and new applications for electrochemistry. The future of electrochemistry is bright, full of promise and potential. So allow the gentle hum of electrochemical processes to lull you into a peaceful and restorative sleep, knowing that the world is constantly being transformed by these invisible forces, working silently and tirelessly to improve our lives and protect our planet. Now, close your eyes and envision the future of energy, a future powered by sustainable and efficient electrochemical technologies. Imagine a world where energy is abundant, affordable, and clean, a world where the air is clear, the water is pure, and the planet is healthy. Electrochemistry can help us achieve this vision. Sleep well. Think of the humble capacitor, a device that stores electrical energy by accumulating charge on two electrodes separated by an insulator. These unassuming components are indispensable in countless electronic circuits, smoothing out voltage fluctuations, filtering signals, and storing energy for brief periods. They're the unsung heroes of the electronic world, quietly performing their duties without fanfare. Now, consider the supercapacitor, an advanced version of the capacitor that can store significantly more energy and deliver it much faster. These devices bridge the gap between capacitors and batteries, offering a unique combination of high power and moderate energy storage capabilities. Supercapacitors are finding increasing applications in electric vehicles, energy storage systems, and portable electronics, paving the way for more efficient and sustainable energy solutions. And what about fuel cells? Devices that convert chemical energy into electrical energy through electrochemical reactions. Unlike batteries, fuel cells do not need to be recharged. They simply require a continuous supply of fuel, such as hydrogen, and an oxidant, such as oxygen, to operate. Fuel cells are a promising technology for powering vehicles, buildings, and even entire cities, offering a clean and efficient alternative to traditional combustion engines. Imagine a future where fuel cell vehicles silently glide through the streets, emitting only water vapor as exhaust. This is the vision that drives research and development in fuel cell technology, a vision of a cleaner, more sustainable future. The Apollo program, a monumental feat of engineering and human ambition, relied heavily on fuel cells to provide electricity and drinking water for the astronauts during their missions to the moon. These fuel cells, powered by hydrogen and oxygen, produced clean energy and a valuable byproduct, pure water, which the astronauts use for drinking and other essential needs. This demonstrates the reliability and versatility of fuel cell technology in even the most demanding environments. Reflect on the electrochemical processes that occur within plants, enabling them to convert sunlight into energy through photosynthesis. Photosynthesis is a complex series of electrochemical reactions that convert carbon dioxide and water into glucose, a sugar that provides energy for the plant. This process is essential for life on Earth, as it not only provides energy for plants, but also produces oxygen, which is essential for animals. Consider the sheer scale of photosynthesis occurring in countless plants across the globe, converting vast amounts of solar energy into chemical energy. It is a testament to the power and efficiency of electrochemical processes in the natural world. The discovery of photosynthesis was a gradual process, with scientists like Jan van Helmont, Joseph Priestley, and Jan Ingenhousz making crucial contributions over several centuries. Their work revealed the intricate details of how plants use sunlight to create energy, laying the foundation for our understanding of this fundamental process. Think about the role of electrochemistry in corrosion, the gradual degradation of materials due to chemical reactions with their environment. Corrosion is a major problem in many industries, costing billions of dollars each year in repairs and replacements. Electrochemical techniques can be used to prevent or mitigate corrosion, protecting valuable infrastructure and extending the lifespan of materials. Imagine the bridges, buildings, and pipelines that rely on electrochemical protection to prevent corrosion and ensure their structural integrity. It is a constant battle against the forces of nature, a battle that electrochemistry is helping us to win. The Statue of Liberty, a symbol of freedom and democracy, is made of copper, a metal that is susceptible to corrosion. Over time, the copper reacted with the environment, forming a green patina, which actually protects the underlying metal from further corrosion. This is an example of how corrosion can sometimes be a beneficial process, forming a protective layer that extends the lifespan of the material. As you continue to relax, consider the potential of electrochemistry in medicine, from implantable devices that deliver drugs directly to specific tissues to biosensors that monitor vital signs in real time. Electrochemical sensors can be used to detect diseases early, allowing for more effective treatment. Implantable devices can deliver drugs directly to tumors, minimizing side effects and improving treatment outcomes. Imagine a future where medical treatments are personalized and precise, thanks to the power of electrochemistry. This is the promise of electrochemical medicine, a promise of a healthier and longer life. The development of the pacemaker, a life-saving device that regulates heart rhythm, relied heavily on electrochemical principles. The pacemaker uses electrical impulses to stimulate the heart muscle, ensuring that it beats regularly and efficiently. This device has saved countless lives and improved the quality of life for millions of people around the world. Let your mind wander to the electrochemical processes that occur in the brain, enabling communication between neurons and controlling our thoughts, feelings, and actions. Neurotransmitters, chemicals that transmit signals between neurons, are released and received through electrochemical reactions. These reactions are essential for all aspects of brain function, from learning and memory to emotions and behavior. Imagine the intricate network of neurons in the brain, constantly communicating with each other through electrochemical signals. It is a complex and dynamic system, a system that is essential for our consciousness and our ability to interact with the world. The study of electrochemistry in the brain has led to breakthroughs in the treatment of neurological disorders, such as Parkinson's disease and depression. By understanding the electrochemical processes that underlie these disorders, scientists have been able to develop new therapies that can alleviate symptoms and improve the quality of life for patients. And as you finally drift off to sleep, know that the principles of electrochemistry are not just confined to laboratories and textbooks. They are an integral part of the world around us, shaping our lives in countless ways. Sleep deeply,